Good morning. Today we can see another example for a single degree of freedom system with applying a periodic load and simulate this with Fourier series. We can remember the dynamic structure utilizing for this case is the simple mass m, where is applied force pt in direction xt, and to this mass is applied also a spring with an value stiffness value kappa of the spring, and damping system with coefficient damping coefficient c. We can remember how it's possible to arrive at the differential equation of this dynamic system. Applied the second law of Newton of this mass. So the force inertia plus la force, the damping force plus the spring force is equal of T. So arrive at this equation 2, where m for the acceleration plus c, where damping coefficient for velocity, plus k for the stiffness of string for the displacement is equal of pt. Pt, in this case, a periodic load. A periodic load, remember, is a force or dynamic stress can repeat identically a regular time interval. And we can define in the period Tp. It is the exact time required for the load to complete one full cycle before starting over, and the frequency is the number of cycles the load complete in 1 second, measured in hertz. So it is the inverse of the period. Frequency is equal divided 40 dp. The mathematical definition, force over time Ft is considered periodic, is satisfy this condition. Ft is equal f dt plus dp. So we can here an example of a periodic load can repeat in different time. We can represent this periodic function with the series of Fourier. So the force Pt is equal at constant at 0 plus the summary of n da 1 a infinity, and other constant n for coseno di n omega 1 bar for the time t, plus n summary of n equal 1 to infinity, other constant Bn for seno di omega 1 bar for the time t, or equivalent in this other form, where n is a number of harmonic, can varies 1 to infinity, plus n is bigger, more exactly is the representation. Omega 1 bar is the first harmonic frequency of the function, where is equal to pi divided for the value TDP, the period TDP, and omega n bar is equal of n for omega 1 bar. The coefficient at 0 a n bn we can express in function of Pt, because the sine and the cosine function are orthogonally. So at 0 is equal to 1 divided for TDP, that's 0 at TDP dp dt, a n is equal of this equation, Bn is equal of this other equation with n can values down 1, 2, 3, infinitive. For the orthogonal property of triangular function, we can state as the following, where n, m are integer. So we can make an example. We can say, before in another video, the triangular function. Now we study the how can calculate the square and square pulse loading, representing this with n Fourier series. This Fourier series is having a period of TDP. It can assume to vary from less TDP divided for 2 at 2 TDP divided for 2. The Fourier series, in this case, we can evaluate in this way, at 0 equal 1 su TDP for integral less TDP divided for 2, other integral limit of integral TDP divided for 2 of integral of PDT. n in function of coseno and of omega 1 bar, e Bn is a function of seno di n omega 1 bar, where PDT is equal a less PD0 for t che can in this interval less the TDP divided for 2 and 0, e positive when t is between 0 e TDP max, TDP divided for 2. Substituting the value of tt from equation 4 in equation 1 and 2 give a 0 equals 0 and a n equals 0, because pt is not the function with t. That is, PDT is equal a less pt than 1 minus t, while a 0 and a n are coefficients of a term in the Fourier series. So the equation 3 and 4 we can write in this way, ma omega 1 bar is equal to pi divided for tp, so Bn become equal less 2p0 for divided for n pi for coseno di n pi less 1, or in this way for n can change between 1, 2, 3, and 5. The Fourier series represented the square pulse is given by this equation, and we can plot for different value then in odd value 1, 2, 3, 5, 7, and so on. Okay, in this way we can see the Python code to represent this equation, and you remember this code similar of the logic of this Python code is similar of triangular periodic load, And okay, we can describe a line for line. And we can see in the line 32, import an amphi is in the library for numerical operation, specifically for handling array and the calculation of pi, sine and cosine. Poi in line 33 import the plotting library to visualize the curve, and after in 34 import the quad function, quadrature, from SciPy. This is used to perform numerical integration, calculating the area under a curve, which is required to find the Fourier coefficient. After defining the integrand for the coefficient, to build the Fourier series, the code must calculate three sets of coefficients: A0, An, and Bn. An for the cosine amplitude, Bn for sine amplitude. The code curve 1 define the base square wave function over time t with the period t and amplitude p. If t minor of t divided for 2, this creates the square shape for the first half of the period. The value is positive and give the value equal of p in the line 42. And the different case when t is bigger of t divided for 2, don't give p1 negative, and return the value multiplied for 1 divided for t. This function will be integrated over one period to find the average value coefficient at 0. In the line 15, define another function to use it to find the value of an so calculate omega, the fundamental angular frequency, and return the 2 divided for t for p1 for n coseno di omega t for n. The same for in the line 62, define the function to this the value of sine, and return the 2 divided for t for p1 for seno di omega t for n. In the line 74 there is the main program. Set p1, set the value, the amplitude of in the period of wave to 1. After print, okay, the parameter in this in the console, formatting them to the 3 significant value. Okay, 3G. At 0, integrate the curve 1 from 0 to 0t. Quad return 2 value, the result, and estimate the error. So ignore their error value, pass the extra parameter to curve. after here preparate the plot of the graph in the line 18/6, and okay, plot this line, plot, sorry, plot ION turn interactive mode. This allows Matplotlib to draw the plot dynamically in a loop without pausing the script. Is in the line 18.3. Here there is create the window to the plot, setting the size, okay, and enabling constrained layout to prevent a subplot from overlapping. N0 divided by create two empty array to size 20 to store the calculate AN and BN coefficient. T value create array of time value from 0 to t, spaced by 0.01 second. This is the x for the plot. Here there is in 19.3 the main calculation loop for plot index. This variable we can change this value to 1 to 21 with the step 2 and start 1. For n in range, loop through the required harmonic up the current limit n, and calculate an1 and bn1, integrate the cosine sine coefficient. Reconstructed to the line 99, reconstructing the wave, output is equal np0 the length, create an empty array to hold the y value of our rebuilt wave. After xt in enumerate t value, iterate for every time step. C equals 0 is equals 0, reset the cosine sine sum for the current time step. For n in range 1 n plus 1, evaluate the various series equation summary, the an coseno di omega t plus bn seno di omega t, and add the offset of the sum and store the final the value in the line 100 set. After, okay, we can there is the line for plotting this calculation, and after save in the line 127 in PDF file. We can see the result of this Python code, and this is the result. The first curve is for the first harmonic, for n is equal to 1. The second wave is the second using two harmonic, with n changed 1 to 3, after 3 harmonic, 4 harmonic, and arrive to 10 harmonic, using also only the odd value of n. We can see the difference between the square pulse exactly in magenta value, and the curve for n, for using the Fourier series to n equal 1, n equal 3, n equal 11. So we can see the approximation is become, for n to infinity, become similar of square pulse exactly value. Okay, we can find also the file of Python code in recipe of GitHub, put in the description. Thank you. Bye.